Hello, today I would like to present my research, and the title is Autonomous Delivery Vehicle in Urban E-Grocery Delivery, a two-tire vehicle routine problem. Nowadays, a lot of e-commerce companies, they provide the same-day delivery or even 2 hours delivery to the customers to meet the requirement of instant delivery. However, these frequently deliveries means that the delivery cost will be high, and it will also cause the environmental pollutions or congestions. Also, this frequently delivery will bring low efficiency of last mile delivery because only a few orders were delivered per trip. So companies now they are seeking the new technologies to make the last mile delivery. Autonomous delivery robots recently received a lot of attention. Here, these pictures show the application scenarios of the delivery robot. The first picture shows that the robots now are testing delivery food on campus. And the second is that it started testing delivery food and grocery in some areas. And third is show that it started makes hospital deliveries. The advantage of the delivery robot is that it can move fast in dense areas, while it is good for environment because it has no emission of gases. However, it also has its limitations. Here, I list some new technology about the robot. We find that most of them can only travel within a limited range, within a limited speed, and some of them can only travel on sidewalks, and also most of them the capacity is limited. So we are thinking, can we combine the advantage of the van with the robot to make the e-grocery delivery more cost efficiently and environmental friendly? Because the van has a large volume and low cost, while the robot can move flexible with no emission. So the objectives of this research is firstly to create an innovative last mile delivery system which combines the traditional van and the ADR to make the deliveries. Second, to develop a new model to optimize the two-tire vehicle routine problem with mixed vehicle by minimizing the transport and emission cost. And third is to develop a new algorithm consist of an improved initialization and an artificial algorithms to obtain the solution. Firstly, let's define the two-tire routine network. We have 2 depots in the first tire and deliver van departure from the depot, visit the assigned satellite and go back to the depot. And in the second tire, the robot start from the satellite, visit all assigned customers and go back to the satellite. In the practical situation, because considering the change of a customer's order, the location of the depot, all satellite might change. So here we still have 2 depots in the first tire. However, the location of satellite S1 changed. Accordingly, the route in the second tire changed. This route change might affect the total transport cost and emission cost. So this research aims to minimizing the transport cost and emission cost under a specific customer's requirement. Here we have our assumptions. Each van and each ADR are assigned at most 1 route respectively, and each first tire trip and each second tire trip must start and end at the same depot or the satellite. In the second tire, the demand of customers cannot be split among different robots, while in the first tire, each satellite's demand could be split among different vehicles. And the total demand allocated to a satellite from the customers must not more than the capacity of the satellite. In order to develop our model, firstly, we need to define the parameters. Here are the set of the nodes and the capacity of vehicles, number of the vehicles, maximum number of routes, and number of the nodes, capacity of the satellite, demand from the customers, unit transport cost, unit emission cost, cost of handling a unit of freight, and travel distance. And then is the decision variables of this problem. We will decide the number of vans traveled in the first tire, and if a robot will navigate a route in the second tire, if a customer will be allocated to a satellite in the second tire, and free flow travels in the first and second tire. So the objective of this model is to firstly minimizing the transport cost, minimizing the emission cost, minimizing the handling cost, and this is restricted to different constraints like the flow conservation constraint, the terminal capacity constraint, the vehicle capacity constraint, and the definition of the variables. Because this problem is complicated, we decompose it into two stages. Firstly, we assign customers to appropriate satellite. And then this problem is decreased to a multi-depot vehicle routine problems. Then we use the heuristics to solve it. And first step is the initialization. We input the location loads of customers and location of the satellite. Then the customers are assigned to the nearest satellite. Considering the capacity of the satellite, we adjust the customer's clustering. And based on the location load of clustering, also together with the vehicle data, the clustered customers are assigned to a vehicle. And at last, the customers are ordered to get a route. Then is the heuristics. In this research, we use artificial email algorithms to improve the final solutions. Because the process of these algorithms is complicated, I'm not give a detailed explanation here. However, I want to focus one operator is the email operator. It consists of vaccination and email selection. Because the artificial email algorithms is inspired by the immunology. So the email operator is different from the other heuristics because it has a memory mechanisms which can be used to improve the solutions. Here, I just use simple illustrations to show how a vaccination is implemented to a VRP. For example, we have two routes to make a delivery, LPI and LPI-F. And according to previous experience, we can get the probability which route has a high probability with shorter distance to make the delivery. So then we can put this information to the algorithms and to guide the search. Then a vaccine is extracted from a priori knowledge of the problem. Based on the vaccination, the second step is the annealing option. So we choose individuals with probability P, and the individuals of fitness of an individual will be improved. And then we will analyze our result. Here, in order to validate the model and algorithms, we test it with two data sets. Here is the characters of the data set. We have the location of depot, number of the satellite, number of customers, number of vehicles, capacity of the vehicles, distribution of the customers, distribution of the satellite. In order to show the performance of our proposed algorithms, we compare it with another algorithm, HJA, that is proposed by Ho in 2008, and we compare them in three aspects: the CPU time, the final best solution, the improvement rate. And we find the improvement rate of our proposed algorithms is superior to HJA for most of the instances. Here are marked bold. And accordingly, the final best solution is superior to HJA. And this can be explained by that we adopt improved initialization steps. However, the CPU time is not as good as HJA. Actually, it takes a little bit longer time. Because in our algorithms we considered in our model we consider more complicated constraint, and we have improved initialization. So this time is acceptable because we have a better final solutions. Another criterion to compare the algorithms is the deviation of the average solutions. Here we also find the deviation of average solution produced by our proposed algorithms is superior to HJA for most of the instances. Only 2 instances are slightly worse in dataset 1. Here we marked bold. And the same in dataset 2, only 2 instances are slightly worse. After we compare the algorithms, we want to see what is the important influential factors on the delivery network. Here we test the 2 types of cost ratios. One is CRTE, that is the cost ratios between transport and emission. Another is the cost ratio between WAN and ADR. And the cost ratio here is generated in different hypothetical scenarios. And finally, we got the minimum total cost and maximal total cost, that is under different cost ratios. Here are marked blue. We also find another 2 important factors. One is the customer's density, another is the depot locations. In this table, we analyze the combination impacts of these 3 factors on the delivery network. For example, here, when customers located in dense areas, when depot move from inner of customer's area to external of customer's area, under this cost ratio, for example, is 0.9, 0.4, the total cost will be increased. Well, under this cost ratio, the CTRVA is equal to 0.7, CRT is equal to 0.3, the total cost almost keep the same. And this is the route choice when customers locate in dense areas 15 by 15. We can see when depot move from inner of customer's area to external of customer's area, the route choice changed. Also, this is under different cost ratios. How about when customers located in sparse areas? When depot move from inner of customer's area to external of customer's area, no matter the cost ratio are, so we find that total cost will increase. And accordingly, this is the route choice when customers located in a sparse area, 80 by 80. When depot move from internal of customer's area to external, the route choice changed. So based on these 2 scenarios, we find that the minimum total transport cost and emission cost of a delivery network will be acquired under a combination impact of the different factors. So according to previous analysis, we have our final conclusions. Firstly, we develop an efficient model to optimize the 2-tier vehicle routine problem with WANs and ADRs. And the proposed algorithms is superior to HJA on the improvement rate and the deviation of average solution, and it can generate high quantity solution to the problem within an acceptable computation time. The total cost and emissions will be achieved under combination factors like layout of depot customers, the density of customers, the ratio between transport costs and emission costs, the ratio cost between WAN and ADR. And this study might provide a technical planning view for a sustainable e-growth rate delivery network when a traditional WAN and an ADR are combined in the last mile delivery. However, the instance generated in this research has a gap from the distribution in actual application in urban deliveries. So future research is required to test the model and the algorithms in more realistic data sets. Besides, the model could be extended when other operational parameters are considered. So here are the publications generated from this research. And this work was supported by the Freight Mobility Research Institute. And thank you for your attention.